Yeah, so good evening everyone. So this course is Basic Electrical Circuits. This is an massive open online course, a MOOC course offered by NPTEL. So the instructor for this course is Dr. Ankush Sharma. He is a professor in the Department of Electrical Engineering at IIT Kanpur. Myself, I am the tutor for this course, and my name is Mayank Arupam. I am a PhD student and a PMRF scholar. I am also from the Department of Electrical Engineering at IIT Kanpur. Fine. So, okay. So in the last week, it is week 11, you learned about state variables, right? So this must be a new thing for you. State variable is something which is new which is new, right? So you might have not heard it earlier. So this is actually the basis of analysis on all computers. All the computers, all the simulators that you work, all the spice simulator, all the simulators that you see nowadays, those which solve circuits or even other control system things, all of them, they work with state variables. Okay, so this is a very general approach to handle complex real life problems. Okay, so one second. Yes, there is someone who wants to join. Yeah, so a quick summary of the week. So you learnt about graphical models. So you learnt about how to represent systems using graphs. Okay, signal flow graphs and all. You also learnt about block level diagrams of a system. So you learnt about how to interpret them. You learnt about how to convert them from one form to another, like conversion from block diagram to signal flow graph, or from signal flow graph to block diagram. You saw all those things, right? Now in the next part you saw about state equations. So these things are new to you, so I hope you have given them due attention. So you learnt about state equations. So these equations are nothing but simply the equations which, sorry, someone wants to join. Yeah, these are nothing but so I was talking about state equations. So state equations are nothing but they are simply the a set of equations which describe the state of the system at particular basically they describe the state of the system. You have a system in consideration, and that system will be represented by, or it will be defined by, some set of differential equations and all. So all those equations, they are called state equations. You also learned about state diagrams, right? So you learned about how to represent the state transition in terms of the diagrams. So you learned about the state equations and converting them into a signal flow graph. So this is what is state diagram about. Fine. So in the next part you learned about state transition matrix. So basically, if you are given a system's differential equation or state equation, now you have to solve it, right? Suppose you know the state of the system at a particular time, and you have to find out what happens to the system as time progresses after some particular time, at some particular time instant in the future. So how will you know that? So that is given by state transition matrix. Okay, so as the name suggests, it relates the, basically it says how the state transitions from at one time to another time. Fine. This is what is state transition matrix. Lastly, you learnt about an application, the real world application of state variable method, right? The example in this course that you learnt about was the state variable method to solve circuits, right? So for circuits, you have seen how to solve circuits using KVL, KCL, and there are a lot of methods, right? But this is a new method, and this is actually widely used. Yeah. So state variable method is something which is widely used, and is used in computers also. Okay, computers use this widely, and it is a very general method. So that is why you must know this method to solve circuits. Not only circuits, but this method is used to solve a lot of real world problems. in mechanical engineering, control systems, power systems, everywhere this state variable method is used because it is a very general method. Fine. So I guess that's it. So anyone has does anyone have any doubt in the week's content, the portions that are covered, that the instructor covered this week? You can ask me if you have any doubt. Otherwise, I'll be moving ahead with the this week's some sample questions that I want to discuss. But before discussing that, does anyone have any doubt? Alright, so moving ahead. Fine, so let's solve questions now. Yeah. So the first question is, in this feedback system, this is a feedback system, right? You see there is a signal, input signal here R, there is output C. You see there is a direct path from R to C, there is a forward path, and there is also feedback path using this factor beta, feedback factor beta, right? So this is the feedback system. So in this feedback system, we have to find the transfer function of the closed loop system, right? So what will be the transfer function of this closed loop system? Let's see this. The answer is already given, but let's solve this. One second. Yeah. So let's solve this question. Question: find the transfer function from R to C, right? Yeah. So how will you do it? So let's represent this node, this particular place. This, let's say this is some x of s. Okay. So what is the equation for x of s? X of s is equal to what? R of s minus. Someone wants to join. Yeah. So what is x of s? X of s is R of s minus, this is R of s, this signal here, and then there is this signal here, right? So if this is C, right? This is C of s. So what is this? This is beta times C of s, correct? So x of s is what? R of s minus beta times C of s, right? This is our equation 1. Now what is C of s? C of s is what? It is x of s multiplied by this factor, right? A divided by 1 plus s tau. So it is x of s multiplied by A divided by 1 plus s tau. This is our second equation. Fine. Now we just have to eliminate this factor x of s here, right? So let's do that. So instead of x of s, we write here, we place x of s in 1 by C of s divided by 1 plus s tau divided by A. right? So if we do that, what will we get? We'll get C of S. Let's remove this. C of S multiplied by 1 plus S tau divided by A is equal to R of S minus beta C of S, right? So this it is I guess everyone understands when I write anything here, it is a function of S here, right? So I'll just drop this off as bracket S, right? So it is implicit that it is a function of S only, since we are taking everything in terms of Laplace transform. So it is C multiplied by 1 plus S tau divided by A plus beta times C is equal to R of S, right? So what we'll get? We'll take C common, 1 plus S tau plus A times beta divided by A is equal to R of S. So, let's remove this of S here. So we'll get again. Now we have to find what? C by R, right? C by R is equal to A divided by 1 plus S tau plus A beta. So this is the transfer function, right? So does anyone have any doubt in this question, the one that I solved? So it can also be easily seen from the formula that you might remember, that for a feedback system, y divided by x is equal to what? Suppose y is the output and x is the input, it is equal to g divided by 1 plus gh, right? Where g is the forward path gain and h is the feedback path gain, right? You see, in this case, forward path gain is a divided by 1 plus s tau and the feedback path gain is beta. So it could have been directly written like this: C by R is equal to A divided by 1 plus S tau divided by 1 plus A times beta divided by 1 plus S tau. And if you solve this, you will again get the same answer that we found out here. Okay. Okay. So I guess there is no doubt in this question. Fine. Moving ahead. Yeah. Next question. So which among the following plays a crucial role in determining the state of the dynamic system? So any volunteers would like to volunteer for an answer here? Okay, so which among the following plays a crucial... Sorry, someone wants to join. So which among the following plays a crucial role in determining the state of a dynamic system? So as I told earlier, state of a dynamic system is what? So it was also explained in lecture very well, right? So what is meant by state of a dynamic system, and what is it? What actually plays an important role in determining the state of a dynamic system? So there are four options: state variable, state vector, state scalar, state space. So you must have learned, right, that in for a system, the state of a system is completely determined by the state variables, right? You must remember it. You might remember it that the state of a system, state of a dynamic system. What is meant by dynamic system? System which is dynamic. Dynamic means which is changing with time. Okay, system which can change its state from time to time. So that is a dynamic system. So basically, that a system which is dynamic has a tendency to change its state from one time to another, right? So that particular system is completely characterized by the its state variables. That is what is state. That is the definition of state variable. A state variable is something which can completely determine the state of a system, right? So I guess everyone understands that the definition of state variable is that it's a It's nothing but a variable which can completely characterize the system's state at a particular time. If you know all the state variables, if you know all the values, all the state variable values, then you can say everything about the state of a system. Fine. So it's just like the biodata of that particular state. Okay, so suppose my name is Mayank. So if someone has my biodata, full data from my life, right? Everything that I've done till now, right from my birth. So if a person has knows everything about me, then basically he can say everything about me. So that is what is state variable. State variable is nothing but you can completely determine the state of a system if you know the state variables, if you know the state variables value. So the answer to this question is state variable. Okay, fine. So again, this is a feedback control system with high gain K. In this case, the gain K is very high. Okay, this is a feedback control system. Again, the same way. You see, from R of S to C of S. This R of S is the input and C of S is the output. You can see there is a direct path like this, and there is also a feedback path which comes from this H of S. So in this case, the forward path with this gain K, it is very high. It is said in the question. So the closed loop transfer function is inversely proportional to what? So let's find out. We will find the closed loop transfer function, then we will see what it is. Yeah. So in this question again, we have to find the closed loop transfer. This question 3. Function from R of S to C of S. Right. So again, what is the formula for closed loop transfer function? C by R in this case will be the forward path gain, right? The forward path gain. So what is forward path gain here? It is K multiplied by G divided by 1 plus forward path gain into feedback path gain, right? So it is K into G into what is feedback path gain? This is H. Okay, this is the transfer function. Now it is said in the question that gain K is very high. So if the gain K is very high, you see what is this? This is 1 plus something, K into G into H. If the gain K is very high, you can safely ignore this one addition of 1 to this number, right? Suppose if gain K is like 10,000, okay, and let's say G into H is, let's say, equal to 1. In that case, what you will have? You will have 1 plus, this is not 10,000, this is 1 lakh, okay? You will have 1 plus 1 lakh, which is again equal to 1 lakh 1. So this is as good as nothing, right? If you add 1 to 1 lakh, you will not be adding much, right? So you can safely ignore. So 1 lakh and 1 lakh 1, they are very close to each other, and if you ignore them, ignore 1, you will not be incurring much error here. So this is a very common practice in engineering, right? Engineering calculations. You cannot always do, in fact, most of the times you cannot do complex calculations, right? There will be a lot of new numbers. A lot of times you will have a lot of complex numbers, right? And a very tedious calculations, and you cannot be expected to do all those calculations by hand. So a lot of times engineers do resort to approximations, and this is a very common practice. You should know how to approximate. So in this case, you see, I am approximating an addition, right? Here I am adding a small number to a very large number, right? This since one is very less compared to this large number, I can safely ignore this addition. Even if I do not add 1 to this number, it will not be much of an error, right? So this can be rewritten as C by R is equal to K into G divided by, so this is approximate, right? So approximate, this is the sign of approximation. maybe this is the sign of approximation. This is k into g into h, right? I have simply ignored this one. So you see k and g are gone, so this becomes 1 over h. Okay, so you see the loop gain c by r, closed loop transfer function c by r is equal to 1 over h. So you can see it is c over r is inversely proportional to h. Okay, so that is what the question was. You have to find out the loop closed loop transfer function is inversely proportional to what. So this is why this is the answer. Okay, fine. Now let's move forward to the next question. So in this question, this is an important question. Okay, so better if I just explain it, the solution. Okay, this is better, right? So this is the question. Okay, you have to find the transfer function between closed loop transfer function between y and u. Okay, so you have to find y by u. Okay, so this is a very this looks like a very messy network, right? This looks like a very messy network, messy block diagram. You see, this is a block diagram of this particular network here, and this looks very messy. So you have got this messy network. So what is the way of solving these questions? So you have already learnt about Mason's rule, right? Mason's rule is actually used to find the transfer function between some particular nodes, right? From one signal node to another signal node. If you want to find the transfer function, that is where you use Mason's rule. Okay, so here also you can use Mason's rule, but Mason's rule is used for it is applicable for what? It is applicable for signal flow graphs, but here it is not a signal flow graph, it is a block diagram. So first you have to convert this into a signal flow graph, right? So you see, this is so for converting this into a signal flow graph, what do you need to do? You need to first define what are the nodes. Okay, what are the signal nodes? So this is u of t, this is incoming signal. Then let's say this signal is x1 of t. Okay, this is x1. Again, then let's say this is x2. Let's say this is x3, this is x4, and then this is yt. Okay, now for this particular question, the SFG signal flow graph will look what? For all the signal points, yeah, like u of t, x1, x2, everything, they have to be represented using what? They have to be represented using these circles. Yeah, they have to be represented using these circles, right? These circles are representative of these signals. So u of s is represented by one circle. This x1 of s is represented by another circle. So first you lay down all the signal points. Okay, so I've laid out circle this and all of the circles, which are representative of all the signals x1, x2, x3, x4, y and u. Okay, after that, what do you need to do? You need to then complete this signal flow graph. Okay, how do you do it? You see, you might remember that in the signal flow graph, all the lines that converge to that particular signal point, they are actually added directly, right? So you see, for this, what is x1 of s here? x1 of s. You see, this is u of t added with this feedback yt. sorry, u of t is coming here and adding to this node, then y of t is multiplied by 9 and getting subtracted here. Similarly, x2 is coming here and multiplied by 3 again getting subtracted here, right? So how do you present it? You represent it like this. So x1 to x2, there is an integration operation, right? And integration operation in Laplace domain is how, what? It is 1 over s, right? Multiplication of one signal by 1 of s. So x1 to x2 is s inverse, okay? So this is how you present it. These arrows, they represent the transfer function basically, or the gain between from one signal to another. This arrow represents that only. This arrows in signal flow graphs, they are representative of a system in between these two signals. So you see, in between x1 and x2 you have a system here, you have an integrator here, right? So that integrator is being written as s inverse, and it is shown using the arrow here. Fine. Now again, this x2 is being multiplied by a 3, factor 3, and then getting subtracted here, right? So what do you need to do? x2, you have to multiply it using -3, and then you have to simply put an arrow here. Actually the arrow should be actually in the middle, not here. So this should be in the middle. When you write it like this, why do you have to multiply it by -3, by the way? You see, here it is 3, but here I have multiplied by -3. So you have to multiply it by -3 because in the signal flow graphs you do not show any plus or minus sign in the addition subtraction at the node. You just make an arrow to the node. All the arrows that are converging to a node, they are simply added, okay? So here you have to if you want to subtract a particular signal, then you have to multiply that multiply a -1 to the transfer function here, okay? Basically this x2 is multiplied by 3 here and subtracted here, so we have represented it as x2 multiplied by -3 here and then added here, okay? These two mean the same thing, okay? Similarly, you see, this y of t here is multiplied by 9 and then subtracted here. So again we will do what? We will multiply y of s by a factor -9 and then simply put an arrow here like this, okay? So all these three, y of s -9 times y of s and -3 times x2 of s, they are added here, okay? Fine. And this is x1. Now similarly you can complete the whole network here, okay? Like this, you can simply complete the whole network here. You see x2 here, x2 is this node right here. It is multiplied by 2 and then that is x3. So x2 to x3 is simply a factor of 2 here, and the arrow is shown in the forward direction because this is how the arrow is shown here, okay? Similarly from x3 to x4, you see there is an addition here, but x3 is directly added here with a simple factor of 1. So x3 is simply added here directly. So I have multiplied it with 1 here, okay? x3 is multiplied by 1 and added to this node x4. Similarly, what is x4? Y of t, which is multiplied by -12. Again, see, this is subtraction here. Y of t multiplied by 12 and then subtracted here. So what we will do? We will add -12 times ys to this node, okay? And then finally there is an integrator operation here also. So x4 to y, you have s inverse multiplication. Fine. So when you do this, you have got your signal flow graph. Now what do you need to do next for application of Mason's rule? So this is what is Mason's rule, right? From Mason's rule, the gain or the transfer function between two nodes is given what? Is given by this particular equation. It is the summation tk multiplied by delta k divided by delta. And what is delta here? So remember, this is 1 minus summation of all the loop gains taken one at a time, then plus summation of loop gains taken 2 at a time. Okay. Then minus of, then you go on like this. And what is delta k? Delta k is delta for that part of the network which is non-touching with the kth forward path, right? So that is delta k. Fine. And tk is the kth forward path gain. So this is all that you need to do here. So since you have this signal flow graph here, the first and foremost thing that you need to do is to find out delta. Okay, and for finding out delta, you have to find out how many loops are there, how many non-touching loops are there, and all. So in this case, you see there are 3 loops, right? You see this is one loop, this here, s inverse time minus 3 is the one loop here. Then there is another loop here, x4 to y like this here. This is s inverse minus 12. Okay, this is another loop. Then again there is the third loop here. So this goes from x1 to x2 to x3 to x4 to y of s and back to x1. Okay, this is another loop. So there are total 3 loops in this case. 3 loops in this case. And how many number of forward paths are there? What is a forward path? It is a path from the input to the output. Okay, where you traverse one node only once. Okay, you do not touch one node more than once. Okay, this u of s to y of s, this is one forward path. So this is the only forward path, by the way. You see, there is no other forward path in this case. Okay, so there is only one forward path in this case. Again, how many non-touching loops are there? So what are non-touching loops? Loops which do not have any node in common. Okay, they are called non-touching loops. So in this case, you see there are 3 loops, right? So this loop is the one, this is another loop, and then there is this loop, right? This loop. So in this case, only 2 loops are non-touching, right? This is this loop and this loop. These 2 are non-touching. Okay, so if you take these 2 loops, you see there is no node which is common for both of them, right? So this is x1 here. So what is this loop? This loop is like this, and this loop is like this. So these 2 loops, they are non-touching, right? So they have no 2 nodes in common. No, there are no nodes in common. Fine. So there is only one non-touching loop. Again, how many non-touching loops are there which are non-touching with the forward path? Okay, that also we have to find out. So this is the forward path from u. This is the forward path, right? U to s, like this directly. U to x1 to x2 to x3 to x4, and then finally y. And there are 3 loops. This loop is one, this loop is one, and this loop is another one. Fine. So this loop is another one. But all these 3 loops, they have some nodes in common with the forward path, right? So you see this loop here. This loop has x1 and x2 in common with this forward path, right? x1 and x2 is a part of this loop, as well as it is a part of this forward path also. Okay, similarly, this particular loop here, this also has some nodes in common, right? It has x4 and y in common. Oh, sorry. I didn't know that my screen is not being shared. I'm sorry. I thought the screen is being shared. Fine. Hey, that is why when people do not say anything, so I do not know, right? So what happened in between? There is no feedback from the people, so I do not know what is going on. Anyway, so I guess now my screen is visible, right? You can unmute yourself and then say something. When I'm talking, I'm looking at my screen and a different screen. I do not always see messages, so it's good if you can unmute yourself and say something. Sorry for that, by the way. I didn't know that my screen was not being shared. I thought I shared it. Okay, fine. So let's go back once more. So okay, so this is the question. Okay, this is the question, and in this question you have to find out the transfer function between u and y. Okay, basically the transfer function from ut to y of t. And transfer function is defined in Laplace domain. Yeah, so the transfer function is defined in the Laplace domain, right? So the transfer function will be what? Y of s divided by u of s. Cool. So this is the transfer function. You have to find out. So this looks like a very messy network, isn't it? This looks like a very messy network, and if you solve it by finding all, you have to define all this x1, x2, x3, x4, everything, and then if you solve this using a lot of, you will get a lot of equation, and this will become simply very complex to handle. Okay, so there is a direct way out of it, isn't it? So you remember Mason's rule. Mason's rule is actually a rule which is used to find the transfer function between two signal nodes. Okay, this is what is Mason's rule. So here also you can apply Mason's rule to find the transfer function. But for applying Mason's rule, you need to first convert your block diagram to a signal flow graph, right? Because Mason's rule is applicable for signal flow graph, not the block diagram. So this is a signal. This is a block diagram, and you have to convert it into an equivalent signal flow graph. Only then will you be able to solve this particular question. Okay, you'll be able to apply Mason's rule in this case. Fine. So how do you find out the equivalent SFG representation, signal flow graph representation of a block diagram? So you first write all the nodes, all the signal nodes. Okay, you write first all the signals. So you name all the signals. So here this is named already, u of t, and this is y of t. So by the way, we will be naming everything in terms of Laplace domain. So this will become u of s, this becomes y of s. Okay, and let's say this is x1 of s, this is x2 of s, this is x3, this is x4. Okay, first you define all the variables, all the signals, and then you represent using what? Represent the signals using this circles, right, in the signal flow graph. So this circles, this is a u of s, this is x1 of s, this is x2 of s, x3 of s, this is x4 of s, and then this is y of s. Okay, after that you simply yeah, so in this case, now next you have to add what? You have to add systems, right? So this is a system here. This integrator is a system between x1 and x2. Similarly, this is a gain of 3. This is also a system. So how do you represent system in the signal flow graph? So you present it using arrows, right? You represent it using arrows, and you write a number at that number or anything with that arrow which represents the system gain. Okay, so like suppose you have to find out what is x1 here. So x1 is a result of addition of ut, then this feedback y of t which is subtracted at this node, and this x2 which is multiplied by 3 and then subtracted at this node. So x1 comes as a result of all of those additions, right? What is x1? So x1 is equal to u of t minus 3 times x2 of t minus 9 times y of t. Yeah, right. So this is, sorry, yeah, so this is x1. Okay, so the x1 that you will, how will you present that in terms of signal flow graph? So you see, from x1 to x2 you have an integrator, right? So that integrator can be represented so that integrator can be represented like this, right? This is the integrator here, S inverse. Fine. So this is the integrator. Okay, so from x1 to x2 you have an integration operation, and integration is represented by S inverse, 1 over s in Laplace domain. This is what is integration. Fine. So from x1 to x2 you have multiplied by S inverse. Now you see, from x2 to x1 you have a feedback factor of 3, and that is being subtracted here, right? So but in the signal flow graph you do not have any subtraction operation. You cannot write minus x1 minus x or 3 minus 3x2. you have to represent it in terms of the system gain only. You have to incorporate that minus sign in the system gain itself, right? Because everything that is, you have no signs plus or minus here, you simply add everything that is coming to a node. Okay, so if you want to subtract something, then you have to include that -1 sign in the system gain itself. So you are multiplying it with 3, right? X2 is multiplied by 3 and then subtracted at this node to result in x1. So we have, what we have done here, we have multiplied x2 by -3 and then simply added to this node. They basically mean the same thing. Similarly, y of t is being multiplied by 9 and then subtracted at this node. So you do the same thing here. Y multiplied by -9 and then added to this node, and that will be x1. Okay. Similarly, x2. What is x2? x2 is simply as written here. x1 multiplied by s inverse is x2, right? Then from x2 to x3 you simply have a gain of 2, simply, nothing else, right? Now from x3 to x4, what is x4 now? x4 is what? x4 is again the addition of x3 and the feedback yt multiplied by 12 and then subtracted at this node. Okay, so what, that is x4. So that is what you do. You multiply x3 by 1, add here, and multiply y of s by -12 and then add here, and that is x4. From x4 to y, you simply have an integration operation. That is again the same thing, s inverse. Okay. Okay. Now, yeah. So now this next thing that you have to do, once you have found out your signal flow graph, if you want to apply the Mason's rule, then what is Mason's rule? Mason's rule is this: if you want to find the gain transfer function between from one node to another node, then you have to simply use this formula: summation of tk delta k divided by delta, where k represents the forward paths. Okay, so k will be, this summation will run for those number of times till the total number of forward paths in this particular network. Okay, so the total number of total number of terms in this particular summation here will be equal to the total number of forward paths, independent forward paths. Okay, fine. So what is delta here? Delta is 1 minus loop gains taken 1 at a time, then plus loop gains taken 2 at a time, minus, and goes on like this. Okay, so you must have already learnt about it. What is delta k? Delta k is the delta for that part of the network which is non-touching with the kth forward path. Okay, and again then there is tk. Tk is the kth forward path. Okay, this is what you have to do. So you see that everything that you want to find out in Mason's rule, everything that you want in Mason's rule is related to the loops, right? So you have to first find out how many loops are there in this particular question, in this particular signal program. There is this one loop here. Okay, x1 to x2 and back at x1. You see the arrows here. This goes here and then comes back here. This is one loop. You see this is another loop. x4 to y and then back to x4. You see the arrows here. Then there is another loop here, x1 to x2 to x3, x4, y, and then back to x1. Another loop. So these three are the three loops. So there are three loops in this case. Now, how many forward paths are there in this case? So what is a forward path? A forward path is a path from the input and to the output, where no node is touched more than once. Okay, that is a forward path. Input to the output. The direction of arrows matter here. Okay, you see from input to the output you can see there is only one forward path, right? So you see this is one forward path like this, u to x1 to x2 to x3 to x4 to y directly. There is no other forward path. This is the only forward path here. Okay, fine. Now how many non-touching loops are there? You have to also find non-touching loops, right? So you see this here. This is one loop, right? x1 to x2 and back at x1 again here, right? But this is one loop here. Okay, you see this is another loop, x4 to y and then back here, right? This is another loop here. You see that these two loops, they are non-touching, right? Because they have no nodes in common. This has x1, x2 and this has x4 and y. This loop contains x4 and y and this contains x1 and x2. So these two loops are non-touching because they do not have any node in common, right? So you have just two non-touching loops. Okay, this is just two non-touching loops here, or basically you have just one pair, right? You have just one pair. Let's write it here. One pair. Okay. Fine. Now you also have to find out how many loops are there which are non-touching with the kth forward path. So in this case you have only one forward path, and you just have to check for that forward path whether you have any loop which is non-touching with that forward path. Okay, so you see in this case this is the only forward path here, right? U to Y, the one that is highlighted in green, this is the only forward path, and you have three different loops. This is one loop, this is another loop, and this is another loop, right? But all these three loops, they have some nodes in common with the this forward path, right? So this loop here, x1 x2, this loop here, this loop contains x1 and x2, and this is also contained in this forward path, right? x1 x2 is also a part of the forward path as well as this loop. Similarly, this x4 and y, these are also a part of the loop, and one second, yeah, this x4 and y, they are part of the loop as well as they are part of this forward path. Okay, similarly you see this big loop here which contains x1 to x2, x3, x4, then y, and then back at x1 here. This is also containing so many nodes in common with the forward path, right? All these nodes x1, x2, x3, x4 and y, all these nodes are actually in common with the forward path, right? So you just have do not have any non-touching loop with the forward path. This is 0. Now you have to find out what is delta, right? So what is delta here? Delta was what? So delta was equal to 1 minus the summation of loop gains taken one at a time, right? So what are the loop gains here? You see 1 minus one loop is this one, minus 3 s inverse, right? This is one loop right here, minus 3 s inverse multiplied by minus 3. This is one loop gain. Similarly, then there is another loop like this, s inverse multiplied by minus 12. This is another loop, and then there is a third loop here which contains x1 to x2, which is s inverse multiplied by 2 here, this 2, then multiplied by 1 here, then multiplied by this s inverse, and then back here. Let's remove these highlights. Okay, yeah, so I was saying that so I was talking about the loop gains, right? So this was one loop, s inverse times minus 3. This is another loop, s inverse times minus 12, and the third loop is s inverse multiplied by 2 multiplied by 1 multiplied by s inverse again, and then multiplied by minus 9, right? So this becomes what? Minus 9 to the minus 18 divided by s square, right? So you have all this 3 here, 3 by s, 12 by s, and 18 by s square. Then you have addition, add what? Summation of non-touching loop gains taken 2 at a time. So you simply have one pair, right? So this is one loop here, and this is another loop here. This is another loop. This is another loop here. This is one loop here, and this is another loop here, which are non-touching. So you simply have to multiply their gains together. So this will be what? This is minus 3 by s multiplied by minus 12 by s. So this becomes 36 by s square. So what is delta? Delta is this. Okay. Now you have simply one forward path, right? So the forward path is only one. That was, again, let me re-say that. this was the only forward path, right? So you simply multiply the forward path is only 1, and you since you do not have any non-touching loops, since you have no non-touching loop with the kth forward path, or the only forward path in this case, this one is the only forward path, and you have no non-touching loop with this forward path, hence the delta for this case will be simply equal to 1, right? And what is t1? T1 is the forward path gain, right? This is equal to 1 multiplied by s inverse multiplied by 2 multiplied by 1 multiplied by s inverse. So this is simply 2 by s square. Okay, this is these are all the terms that we require for applying Mason's rule. So when you apply Mason's rule, finally this becomes t1 multiplied by delta 1 here. This becomes 2 by s square, right? So this is what? This is t1 multiplied by delta 1, and this is what? This is delta. So Mason's rule, remember, this is equal to tk multiplied by delta k divided by delta, right? And k is how many k's you will have, how many terms in the summation you will have. The number of terms in the summation will be equal to the number of forward paths. Since you have only one forward path, hence you have only one tk t1 multiplied by delta 1 divided by delta. So what is t1? T1 is 2 by s square, delta 1 is 1. So you simply multiply 2 by s square here, and then in the denominator you have this delta. Delta is this, okay? So if you solve this, you will get this answer here, 2 by s plus 6 into s plus 9. Okay, so any doubt in this question? This was kind of a long question. I wanted to discuss it well, because this is an important one, application of Mason's rule. So are you clear on this question? Okay, fine. So let's move on to the next question, the final question for today. The signal flow graph is used to find the what? There are 4 options here: stability of the system, controllability of the system, transfer function of the system, and force of the system. Why do you use signal flow graphs? So as I said earlier, just in the last question, signal flow graphs is mainly used to find to apply Mason's rule. Okay, Mason's rule is applicable only for signal flow graphs, and hence what is Mason's rule used for? It is used to find the transfer function between some particular signals, right? From one signal to another signal, you have to find out transfer function, and for that you apply Mason's rule. Okay, so a signal flow graph is mainly used for finding the transfer function of the system. Okay, the correct option is the third option. Any doubt in this question, or any part in general from today's discussion? So I have discussed everything that I wanted to discuss today. Okay, so if there is no doubt, then thank you. Everything has been discussed today, and thank you for joining today. Thank you for joining. That's all for today. You can leave now.